Okay guys, thanks for coming along. My name is Stephen Merity and I'm a data scientist at Common Crawl. And you might not know yet what Common Crawl is, so let me help you with that. We're a non-profit that we basically make web data freely accessible to anyone. And by web data we mean that we have crawl archives released at the moment every month. And as an example, the February crawl archive is 1.9 billion web pages, which is about 154 terabytes uncompressed. So we're talking about a large amount of data every month, the exact sort of thing that NLP practitioners want. We also release this totally free. So Common Crawl is actually a non-profit. And our goal really is just democratize access to this data set. We don't add any intellectual property restrictions on top of what is already provided by the internet itself as you scrape. And all of this lives on Amazon public data sets. So if you were to spin up a cluster right now and start running an experiment, your compute infrastructure is sitting right next to the storage infrastructure. If you wanted to download the data, which many universities have, for example, you can also do that completely for free. Now, we release the data in 3 different formats. One is called WARC, which is the kind of raw responses themselves. It has the HTTP response headers and then the response data itself. We also provide 2 different formats for kind of different use cases, which are substantially smaller than the originals. One is called WHAT, which is just a metadata format. If it's, for example, a HTML page, we'll actually parse through the HTML page, pull out the title, pull out any of the links, any of the attributes on top of that, any references to JavaScript or CSS, for example, and store that as a JSON file. So we do that for each and every one of our 1.9 billion records. And the third format, which you guys are probably most interested in, is the WET format, or the extracted text. So the extracted text is released alongside the crawl archive every month, and it's basically immediately available. It tries to cover the majority of use cases. So you're not going to see, say, a whole lot of specific NLP conversions in place. We're trying to get the kind of majority use case there. And so because of that, there's no distinction between, say, the header, navigation, or content. We don't remove boilerplate at this level, and we don't reformat the text to appear as exactly as it would in the browser, so paragraph tags, for example. But even given that, it's an incredibly useful resource to start off with, and if you wanted to actually reformat the data in some way, you have all the raw HTML there for you to use as well. So before I get kind of further along, I thought I might frame this in terms of the origins of Common Crawl and why we think it's so important. So Common Crawl was founded in 2007 by Gil Elbaz, and Gil is best known for his work at Applied Semantics. He created a company which was then acquired by Google and then became one of the main engineering directors at Google. And during that time, he discovered how powerful the web was as a data set. And the issue is, the web can be used in so many different ways. You obviously have the kind of immediate use cases of the search tools, for example, indexing the web, but then all of the bits and pieces that build on that, the idea of hyperlink graph analysis, metadata extraction, kind of the list keeps going on and on and on. And this is only possible if you actually have access to the web as a data set itself. Now, the thing that was really tragic for him was that at that time, really, Google and Microsoft were the only players who had this sort of thing. If you're in academia and you want to do kind of cutting-edge research, your main option really was to just go and intern with them or to do a joint project with them. You weren't able to go off and do something yourself. Again, if you're a startup or a commercial entity, the barrier to entry is so incredibly high if you need to do all of this crawling. So he started Common Crawl with the goal of democratizing and simplifying access to the web as a data set. And whilst we're talking about some of the use cases that we have here today, I'd also ask you to kind of keep in mind the idea of open data and open source and the parallels between them. So open source is already an incredibly well-established field, and open data is really just beginning at this stage. And the thing is, for us in particular, data powers so many of the different algorithms that we have in this field. Without data, most of our algorithms are quite useless. And we need to consider the fact that we need an even playing field for enabling innovation across all these different industries, in academia, in startups. And one of the tragedies is that if you look at, say, a lot of the research published by Google and Microsoft, they will have a small kind of toy data set they run their algorithm on, and then their enormous internal proprietary data set that no one has access to. That means you can't replicate the results, and it really, that is one of the major stoppers of innovation in our field. And finally, one of the kind of fun things is that more data can beat better algorithms. Most of you probably know the Banco and Brill paper, but they showed that a very stupid machine learning algorithm given a huge amount of data beats handily the smarter algorithms given a smaller, better curated data set. So with all of that, how can you use Common Crawl for NLP? The web's largely unannotated, and that's usually not the sort of thing you want for NLP, right? So I'm going to be talking about two specific ways you can go about using it. The first is to use extracted text for unsupervised algorithms. Pretty clear, pretty obvious. The second, though, is filtering this huge data set into either a semi-annotated or an annotated data set. Now, the issue is that performing that filtering and getting a high level of precision is usually quite a lossy process. But here you have the advantage of the fact that we have such a big data set to start with. And even if we filter it immensely, we still end up with this smaller data set that's still gigabytes or terabytes in size. So I'm going to be looking at a few different examples. The first is Ngram language models and also GloVe. So one of the obvious considerations here is that given a huge amount of raw text, easiest thing you can do is grab Ngram counts and language models. And that has actually been done for you to use. So a team from Edinburgh, Stanford, and Allen BV went ahead and actually processed all the text that Common Crawl has produced and ended up with 975 billion deduplicated tokens, which is an enormous data set in and of itself. Even if you then compare it to, say, Google Ngram data set, which many of you have probably used before, which was 1 billion tokens in size. On top of this, there are actually some advantages of the Common Crawl-based Ngram data set compared to the Google Ngram one. There are some kind of, I guess, technical things such as the inclusion of incredibly low count entries. There's also, more important one, deduplication or reduced boilerplate, which wasn't actually included in the Google Ngram's data set that was released. So you can imagine a whole bunch of, say, navigation terms like about us or contact us are hugely overrepresented. Now, to kind of go back to the issues with internal proprietary data sets versus what we'd want from open data, Google has shared a deduplicated version in limited context, but it was never actually publicly released. So it was shared with a few collaborators, a few different papers, but it isn't something that most people can get their hands on. I was also going to just mention the fact that they used the wet format. They didn't reprocess all of the HTML responses themselves. And they said that the advantages of structured text don't actually outweigh the extra computing power needed to process them. So this was the exact sort of use case we were hoping to see when we released all of this data, and also the kind of different formats that the data is available in. So to give you an idea of the sizes that they had, this is before they did deduplication. They had 23 terabytes of English, a terabyte of German, Spanish, 900 gigabytes of French. So you can see there's a large language skew. We're working to fix that. But one of the great things is that even though, say, only 0.14% of the corpus was in Finnish, the corpus for Finnish was 47 gigabytes in size. So they're still far larger than most algorithms are actually running over. There are 42 languages with over 10 gigabytes and 73 languages with over a gigabyte of data. So you can imagine this would be a great thing for, say, testing language detectors or other different things like that. So when they performed the sentence level deduplication, it ended up removing about 80% of the English corpus. A huge percentage, but again, consider the fact that most navigational elements are in English, most other things like that. It's lower for other languages, and all this was in line with previous work in deduplication on web data. So before pre-processing, they ended up with 23 terabytes of English. After pre-processing, it was 5 terabytes, which is where they ended up with the 59 billion lines or 975 billion tokens they used for the language model. So given this data set, they actually had substantial improvements in complexity compared to a lot of the other corpuses you might be using or seeing in the literature. This is actually a shortened version. There's a number of other different things. I just wanted to get all in one page. The main thing is, however, perplexity, so the ability of basically being able to guess the next word as it comes up in context, is substantially better using the Common Crawl language models they developed. And additionally, the out-of-vocabulary is substantially lower. So far better results than a lot of these previous models. And they then applied this to a machine learning task, a number of different languages, but the example here is from English to Spanish. And they found that even though the web data is incredibly noisy, or, well, I said incredibly, they said quite, even limited amounts give improvements. And they basically showed that kind of the more they added in, the better the blue score actually got. So that's kind of showing you the fact that even though web data are traditionally very noisy, it is useful even in a task like statistical machine translation, where you really usually have to worry about these issues. The great thing about this is all of this project data was actually released at statmt.org/ngrams. You can go ahead and download either the raw text split by language, the deduped text split by language, or the resulting language models themselves. So if you have a task that you want to use, here are 3 different ways of using it, and you don't even have to touch Common Crawl. A lot of the work has already been done for you. This work is actually being used in a number of different papers from this point on. So this is one of the great things that we see. A lot of people who actually build on Common Crawl end up releasing the data sets that they produce back into the wild. Yep?
What's the license on that data?
I believe it's basically the same as the Common Crawl license, where they don't add any intellectual restrictions, but you probably want to check that on the site. The second example is, I'm sure many of you have probably seen word vectors today, or you'll see it tomorrow. So I won't go through it in too much detail, but the idea behind word vectors is that we want to represent basically dimensions of meanings with words. And one of the cool things about it is you can say, take the word vector for king, subtract man, and add woman, and it should be approximately equal to the word vector for queen. And a lot of this is based on kind of contextual clues. So GloVe is research that came out of Stanford recently, and the reason that I'm mentioning it is that they actually use Common Crawl. So these are kind of 2-dimensional projections of these word vectors, and you can see at the top, it's generally female nouns, at the bottom, it's male nouns. So you can see that kind of dimensionality preservation in place there. Same sort of thing happens with, say, verb tenses, for example. So slow, slower, and slowest is very, very close to short, shorter, and shortest, and has the same sort of structure. Now, one of the really cool things about this is that all this is trained on non-zero entries of the global word-word cooccurrence matrix. Basically, they just take account of how all the words are next to each other. And populating this matrix only requires a single pass over the data, and all the subsequent training is actually far faster. So surprisingly, GloVe is actually faster to train than online window-based methods such as Word2Vec, but it will probably take a whole bunch more memory. Given that, they actually then looked at how it worked on a number of different tasks, so semantic and syntactic. So semantic being Athens is to Greece as Berlin is to Germany, syntactic being dances to dancing as fly is to flying. And they basically found, well, surprise, it works quite well. What the real surprise was is that they compared it to using a few different corpora. First is Wikipedia from 2010 and 2014, and the second is GigaWord. Now you can imagine Wikipedia is an incredibly well-curated data set compared to the rest of the internet at large. The internet's full of all sorts of kind of horrible grammar, all sorts of terrible pronunciations or sentences, things like that. So you'd expect it to probably perform worse on these sorts of tasks. But it turns out that Common Crawl actually outperformed all of the other different corpora in that data set. And I mean, one of the main reasons for that is quite likely just the fact that we had so much more training data. With Wikipedia 2014, it was 1.6 billion tokens. With GigaWord, it was 4.3. And Common Crawl was about 10 times that at 42 billion tokens. But the fact that it actually outperformed it on a syntactic level is kind of clear and obvious why that would happen, but on a semantic level is far more surprising. And you can imagine also that the coverage of domains is also far better with Common Crawl. So GloVe using 42 billion tokens from Common Crawl actually outperformed Word2Vec with 100 billion tokens from Google News. Again, Google News being the kind of better curated resource. And the other really cool thing is that they actually proved the scalability of this model. So the largest GloVe model they used was 840 billion tokens from Common Crawl. That's 20 times the size of the data set that we actually just saw then. The reason that they used this data set rather than the other one is that the 840 billion token data set was just normal casing. The other one they all lowercased, so it wasn't directly comparable to the other academic models that they were looking at. And again, on top of this, the same sort of thing happened as with the Ngram data before. They released all the source code and also the pre-trained models online at the Stanford website. So you can go online right now and grab 300-dimensional word vector representation from 840 billion tokens of Common Crawl. I'd also mention one extra thing, which is if you are going to be using word vectors, you probably want to mix and match as much as possible. So this is work from automatic noun-compound interpretation using deep neural networks and word embeddings. And they basically found that by combining three different representations of word vectors and using that for their final task, they were able to get substantially better results. The other thing that was interesting was that the more data that was provided to the word vector representations themselves, the less fine-tuning was needed to actually get the best results in the end. So again, more data, less problems, sometimes. The second example that I'm going to be running through is filtering. So as I said before, when you have such a large data set, you can quite commonly filter it down really quite aggressively, trying to keep precision as high as possible and still end up with good results at the end and a huge data set to use. One of the first examples I'm going to be talking about is the idea of using Common Crawl for producing gazetteers for NER. So for gazetteers, we want the widest variety of topics possible. You want to be able to cover as many domains, newswire, say entertainment news, so on. And a lot of the time, we only really have access to newswire text, which is quite a problem considering the performance losses that we get from domain generalization. The second is that we want to keep these gazetteers modern and up to date. You're not going to find anything even relating to the iPod in a lot of the newswire text that we're looking at, let alone the iWatch, which only came out a few months ago, well, a week ago, whatever. And the third is we want to actually capture relationships between these similar words for disambiguation purposes. So many of you might have seen Google Sets from a number of years ago. It was a Google Labs project that is now sadly being deprecated. And the idea behind that was to use web tables as a source of gazetteers and relations. So you could enter a query for a single word cat and end up with it returning dog, bird, horse, and rabbit. But if you ended up querying for cat and ls, Unix command line tools, what you got back was another list of Unix command line tools, cd, head, cut, vim. And all of this was powered by web tables. Now, as I said, this was sadly deprecated by Google. You could only access it through an API beforehand anyway, so there was a limited amount that you could do for, say, NLP research. But these days, you have a few different options. You could go through and do it yourself, or you could just rely on someone else who's done it for you. So Web Data Commons are a great team. A number of universities have kind of partnered together, have taken the Common Crawl data set and built on top of it. And one of the things that they've produced is the web tables data set. They extracted 11.2 billion tables from all of the HTML files that we had, filtered it down to just keep the relational tables via a trained classifier, which had been kind of previously covered in other research. And the idea then was that they had very, very, very high precision on this trained classifier, very, very low recall. Even though they only kept 1.3% of the original data, they still had a hugely useful corpus at hand of 147 million relational web tables. And they ended up releasing this again, like all the previous work, for anyone to use and anyone to download. And it was about, I think, a gigabyte in size, so really quite a small amount of data in the end. Now, the popular column headers that they have are things like name, title, artist, location, model, manufacturer, country, the exact sort of things you would want for, say, your NLP parsing system to have in a gazetteer. And it just keeps going on as well. ISBNs, a huge list of things that would usually be incredibly difficult to pull out. And for me, these are kind of some of the examples. My favorite is camera models. I enjoy photography, but even me trying to kind of parse some of the sentences that have camera models in them is next to impossible. So things like Canon EOS 30D, Canon EOS 50D, Nikon D80, you can imagine how challenging that would be for a NLP parsing tool if it didn't have a gazetteer list to rely on. The other things are things like movies, which are all modern, music albums, which you probably might not be able to find an easy source of, or also footballers, which I'm sure there are some NLP applications that desperately want a gazetteer list of footballers. So to continue on with the kind of trend of filtering down and just using something kind of simple to kind of pull out this data set, we have dirt cheap web-scale parallel text from Common Crawl. And this is a ridiculously simple idea. They processed all the text from URLs of the style website.com/a language code. So /fr/en. They then went and looked at all of the different web pages that they've found, and if they had the same URL other than just the language code, they assumed that they were parallel text. I believe they did a few extra steps at the other end to kind of double check, but that was literally the level of filtering that they did. And the quote from the paper, which I absolutely love to say, is that nothing more than a set of common two-letter language codes, we mined 32 terabytes in just under a day. So this is all on AWS. Don't believe the numbers in the paper. They didn't use spot instances. So if you are going to be doing work on AWS EC2, I highly recommend spot instances. It'll cut down your cost by like 10 times. But basically, they did all this in a day on the AWS cloud. And from that, they ended up with really quite a kind of rich data set to use. They had, in this case, the source language is a foreign language and the target language is English. They had things like 10 million segments of French, 7 million segments of German, and the list goes on, even to some kind of very, I guess you'd consider them less likely to be seen languages such as Farsi, Telugu, and Somali. And all of this, of course, is useful for machine translation because it's usually so hard to get anything for machine translation in quantity. The other thing that it's really useful for is the fact that a lot of the time you'll see Europarl and United Nations used as corpora in statistical machine translation, which is great. They're large data sets, they're incredibly well curated, incredibly well written, but they're very specific to the genres at hand. You can imagine it covers a lot of things such as international rights, education, training, schools, things like that. But it isn't going to be talking about vacations or Yosemite Park or, say, cars or car dealerships or body lotions, things like that. Things that people who want a statistical machine translation system for general cases would really want covered. So they found that the resulting improvements of up to about 1.5 BLU on the standard test data sets, so data sets within, I believe it was a Newswire domain, but they had 5 BLU improvements on test sets outside of the Newswire domain. Again, showing the issues with kind of like domain generalization, the losses that are incurred if you don't have training data from those different data sets. And all of this was, again, with minimal cleaning and filtering, which still resulted in substantial improvements to the statistical machine translation performance. And in the end, I'm sure you're wondering what kind of the appearance of the data was in the end. They did manual inspection across 3 different languages and found about 80% of the data contained good translations that they would be happy to feed to the machine learning algorithm at hand. And that is, I mean, really quite a high level if you consider the fact that we're pulling out the web at large. So onto, I guess, a smaller and easier kind of topic to think about. It's extracting US phone numbers. And this is kind of, I guess, more along the lines of information retrieval, but I wanted to show kind of the possibilities at hand when you have data sets of this size. So someone at Yelp basically decided one day that they wanted to use Common Crawl to help match businesses from Yelp's database to the possible web pages for those businesses on the internet. So in the end, they extracted 748 million US phone numbers from the Common Crawl December 2014 dataset, and that was just done using regular expressions over the extracted text format itself. So really quite a simple programming job. So simple, in fact, it was 134 lines of Python. The total time for that as well was only 1 hour. They used 20 C3 8X large machines on AWS. Yes, scarily large machines, but 20 of those for an hour, if you're, say, using spot instances, is really quite a small amount. In fact, it's only about $11. Additionally, the $11 is kind of a high price point because they were using Python, not necessarily known in the community for its speed. And also Elastic MapReduce, which if you're using spot instances, Elastic MapReduce is almost as, I think it's either as high or slightly more expensive than the cost of the machine that you're hiring itself. So you can imagine getting this down to even like $4 or $5 if you're really kind of gung-ho about it. So they matched this against Yelp's internal database, and they found that 48% of the returns that they had were exact URL matches for what they had on file, and 61% had matching domains. So you can imagine people either doing kind of specific URLs to, say, a subpage on their website or whatever else. They didn't go into full detail on this, but it's really quite promising when you can spend 134 lines of Python in an hour to find out something like this. So there are more details on this and the full source code as well on Yelp's blog post, which is called Analyzing the Web for the Price of a Sandwich. I wouldn't pay so much for a sandwich, but fine for them. And one of the really quite interesting ones that has come up recently is Wiki Reverse, which was created by a volunteer called Ross Fairbanks, literally just for fun. So that's one of the, I'll kind of go off on a bit of a tangent. That's one of the things that I really, really love about the fact that we've kind of got this partnership with AWS, which is that, you can do the experiment that we just saw for $10.60. And we have a whole bunch of people just volunteering their time and interest just for the fact that it's something they'd like to do, and it's really only a very small amount of money that they actually have to spend doing it. So we feel this is opening up this data set to a huge number of different use cases and a huge number of different people who might want to be using it. I'll also mention that this work was done using the MR job framework, which is a brilliant framework if you are, say, trying to teach people MapReduce, because it's all Python. If you're running it locally, it just runs on your machine. You don't even have to install Hadoop. But you have a single command line option, and it will send the job off to AWS to be run on a huge cluster on kind of whichever data sets you might want to be using. So a really good kind of educational tool. Anyway, to go back to WikiReverse, this was all done by a volunteer just for fun. I think it was $80 in total at the end, and I think he did it in Ruby. So again, not exactly a language known for its incredibly high performance and incredibly low cost. So the task was to find hyperlinks that link to Wikipedia from the web at large. And the resulting data set was over 36 million links. And we were actually surprised by the size of that. It seems fairly small. But we were actually looking at kind of similar work that we found done by UMass and Google Research called WikiLinks. And they used it as a source of a large-scale cross-document co-reference corpus. And they only ended up with 40 million links, though they did a fair amount of filtering. Specifically, I believe it was making sure the web page wasn't an exact copy of Wikipedia, and also making sure that it wasn't just kind of a transitory mention in the text. They wanted a large chunk of text for them to be able to look at and consider it as a document actually related to the entity that they're linking to. Again, as before, all of this code and data was actually released online at wikireverse.org. And for $80, the fact that you can pull this data set out and really have this kind of fun exploration across the web at large is amazing. For the fact that without, say, a resource like Common Crawl, the idea that you would actually crawl all of these web pages just for this one specific task of WikiReverse would be a little crazy. It would mean a huge amount of money spent, a huge amount of pain, versus I think this was done in a weekend compared to the hour beforehand. So all of these derived data sets are basically there for you to use. These are only a few of the ones that really focus on natural language processing. So the parallel text for machine translation has been used in a wide number of academic papers. Unfortunately, it hasn't been released just as like a download you can grab right now online, but I'm sure the authors are very happy to share it. And it's been used in a very wide variety of machine translation papers. The Ngram and language models data set is available for you to grab right now. Don't try it over this internet connection, it'll probably die. But again, 975 billion tokens, not just comparable to Google Web 1T. In some ways, it's substantially better for a lot of the tasks you'd be looking at. The WDC web tables collection, which I highly recommend you grab just for the fact that gazetteers are so useful. And then some of the other ones which aren't so specific to NLP, WikiReverse, which we've already covered, and then also the WDC hyperlink graph. If you are interested in performing analysis over 128 billion edges, go ahead. There are some interesting papers. Check the Common Crawl blog. You can actually process that data set on your laptop. Admittedly, I think it takes 13 hours, but if you can do it on your laptop, that's really quite an impressive feat. And on top of that, though, there are a million use cases waiting to be discovered. Mix and match either things from academia or industry that you've seen but didn't think were necessarily possible without a data set of this size, or just your specific use cases that you've got and pulled out. So one which, if anyone is interested in a bit of challenge or knows a PhD student who's kind of lost for ideas, that I've been thinking about is parser training data. You want automatic acquisition of it because the more data you have, the better your results generally are. So this is working off a paper called Automatic Acquisition of Training Data for Statistical Parsers from 2008 by Howlett and Curran. And it's a brilliantly simple idea. And the idea is that you use a knowledge base of either facts or incredibly simple sentences, such as Mozart was born in 1756, to help you parse the horrific sentence down the bottom. And the way you do that is you apply dependency constraints. So you know from the first sentence and from the fact that basically all of those words are in the second sentence, that you want to have that dependency at the end, that Mozart is the subject of born, and born occurred in 1756. So given that dependency constraint, a lot of parsers actually have a substantially higher chance of being able to successfully parse a sentence at the end. You can check the paper for full details, but it's a concept that works, and it actually worked quite well. The issue at the time was that these were being pulled out manually. They didn't have a huge collection of web data to come across, and the fact is that it was difficult to kind of reconcile a knowledge base of facts with web pages that might have those facts on them. But if you then kind of jump back to Wiki Reverse and the fact that WikiLinks is kind of the inspiration for that, and it's a cross-document co-reference corpus, you suddenly have Wikipedia, which has literally a box that contains that fact, that Mozart was born in 1756. You have a whole bunch of pages that link to Wikipedia, specifically the article on Mozart, and you can go and actually grab those and start pulling out these sentences for use in statistical parsing. So this is the sort of thing which would be brilliant to see and is really possible. You're just kind of piling together 3 different data sets that are now easily available to you. Which kind of brings me to my wrap-up point, which is, why am I so excited? It's because open data is catching on. We have all of these data sets now, and I mean, Common Crawl really released just the simplest possible of formats. We release the raw data, we release a bit of metadata, and we release the extracted text. But from all of this, it's already starting to kind of even the playing field for academia and industry. One of the things that really excited me recently was that Baidu used Common Crawl for its deep speech recognition system. And this is Baidu, they're a search company. They have an internal corpus that they can use. Possibly not so strong in English, but still, the fact that they're using Common Crawl is a really great thing, not just for the fact that they're using us, but also that the research can be replicated far more easily. And the same with all these other things. Probably doesn't surprise you that Google is the starting point of all these 3 bullet points. But a lot of the resources before that, it was only really possible for Google or Microsoft to release because they're these powerhouses of data, starting to become a more democratized process. So you have Google Web 1T with Bucket All's Ngrams, you have Google's WikiLinks with Wiki Reverse, and you have Google Sets with the WDC web tables. So for me, this is incredibly exciting. I feel that open data is really something that is required to push forward the NLP domain and the machine learning domain, and that without it, innovation really will be stifled. So I believe we've got about 5 or so minutes for questions. If you're interested, there's a whole lot more to read at Common Crawl, and otherwise I'm going to be here for the rest of the day. Yep. Yeah, the focus really is HTML. There are a handful of different documents, and surprise, there's also another data set you might be interested in. I can't remember the name of it because it was a very strange and esoteric name, but it's a collection of binary documents that they used Common Crawl, pulled out all these different binary document links, and then downloaded them to a separate data set. But yeah, exactly. For us, though, we really just focus on HTML. There are a few other things that end up in there, and there are a few other file formats that we do try to grab if we happen across them, but most of the time we really are just focused on HTML. Yep. Yeah, well and truly. So the question was basically, do we have any plans for performing deduplication and boilerplate reduction ourselves at kind of the whole corpus level? And the thing is, we would really love to do that, but I guess there are a few technical questions to go along with, and then there's also kind of the broader question of exactly what do we do and how do we do it. So one of the reasons that the extracted text format is the way that it is now is that it's really the remnants of creating the metadata format. So we go through and we parse the pages for links, for HTML header information. And whilst we're doing that, we also just kind of throw all of the text together somewhere else. The issue is that even that is really quite an exhaustive process. I think it takes probably a week and a half or so each month that we're doing it. And to do any of the more kind of complex text extraction tools, a lot of them, I mean, are really just not made for the scale that we're running at. They'd be far too slow. But to get that as a data set would be something we'd be interested in. The other question, though, becomes what exactly do we do? Many people are interested in boilerplate, for example, or say structured text. Then it becomes a question of what format do we store it in? What do we remove? What don't we remove? And in fact, it's one of the kind of very strange questions for the corpus in general, for the fact that as a web corpus, a lot of people ask us how much spam do we have? How much porn do we have? We certainly do have spam, but we try and keep it down to manageable levels. But it's also sometimes the strangest question for the fact that spam is kind of a genre in itself. People have used the Common Crawl corpus to pull out spam. So removing that isn't necessarily, at least in its totality, isn't necessarily in the best interest. Yeah. Right. I guess it probably depends on the scale. You could also have it be performed at kind of the client side if you want to consider it that way. Or something else like that. Again, yeah, the issue is just so many different formats, what to remove. Yep. Glad you asked. I won't pull up the web page now, but Web Data Commons actually pulled out a corpus of microdata RDFA from, I think it was 4 or 5 billion web pages. So they have a huge collection of microdata. They also update these corpuses reasonably frequently, so they can also see how this kind of metadata formats change over time and what is actually captured in it. So yeah, check that out at webdatacommons.org. Yep.
So for someone who just wants to start out something new on the Common Crawl database, what would you recommend as kind of a basic experimental test? I want to run something on EC2 or AWS to get access to the Common Crawl data. Let's say I want to filter to find all of the addresses. It's more like addresses on
Yep.
similar to the phone system. What would you recommend?
Yeah, so the easiest thing to actually do is you can either grab the code from the phone number example itself. We also have a MR job framework that's specifically made for handling Common Crawl, which you can throw straight up onto EC2 and have running. That handles a whole bunch of kind of small issues you probably don't want to deal with and just leaves you with Python in the end. And that's a really good way to start off. Again, Python is not great for the speed that it runs at, but it is a really easy and fast way of prototyping and making sure that it's this is a good thing for the task at hand.
Right.
Yeah.
Anybody have a question?
Brilliant. Well, as I said, I'll be around, so thanks, guys.